In this video, I will be demonstrating a technique for solving geometric equations using logarithms. So let's go back to the Diamond Lake rainbow trout example. One question we could ask is, what year will the lake rainbow trout population reach 600 fish? And keep in mind, we're assuming, like before, get my pen. So our assumptions for the model were one, that there was a constant growth rate, of 6% per year, and also that the initial population, or what we're calling P0, is equal to 50,000 fish. Now you might recall this graph that I had in a previous video on this about this problem. And one of the reasons I want to show this graph is I want to demonstrate how we could use the graph to estimate how many years it would take to reach, for the rainbow trout population to reach 600,000. So if I look at the y-axis, or the vertical axis here, there's 600,000. So I could project across horizontally. Of course, there could be some, this is an estimate because I'm sort of eyeballing it here. And it looks like that's right about at this point. So then I would try to project straight down from that point. Whoops. And I don't know, I'm getting somewhere between 44 and 45 years. So I might say, I might estimate from the graph that it's going to take about 44.5 years. But I also want to show you what the main reason I'm making this video. This is one way to get a good idea. And actually, I'm looking at this now, and I think actually my horizontal line, or my vertical line here, is kind of off a little bit. It might actually be more like 43 and a half years or 44 years. So, but the point being is, when I look at the graph and I try to estimate using, by projecting across and down, there's obviously going to be some discrepancy in how one person does it versus another person. So I want to demonstrate another way, analytical way, to do the same problem. And what we need to do this is the idea of a logarithm. And I'm not going to spend time really talking about logarithms per se. It's really an algebra topic. For contemporary mathematics, I mostly want students to be aware that there's a technique for solving this type of problem. And so go back. Whoops, I wrote that wrong. Let's go back and look at the general form of the geometric growth equation. So it looks like that. And in this case, we would write, whoops, I keep doing that, P sub n equals the initial population in this case, which was 50,000. And our growth rate is 6%. Now we have a number here we're shooting at. We're interested in knowing, when will the population reach 600,000? So I'm going to replace the P sub n on the left side of the equation with 600,000. I'll add 1 and 0.06 together to get 1.06. So now we have an equation that has one unknown value. And generally speaking, when we have this situation, then we can, there are multiple different techniques to use to solve equations that have one unknown. This particular case, that the unknown we're looking for is an exponent. So you have to be careful here. This is not, the unknown is not involved with like multiplying the 106 or anything. So, we're not going to do any division here. Well, actually, I take it back. We can and we should do division as our first step, as a simplifying step. And the reason is because there's a 60,000 on this side and a 50,000 here. There are a couple of constants in the problem that we can simplify. So I'm going to start off by dividing both sides by 50,000. And that's going to leave us with 12 on the left side. It's fine to do this calculation on your calculator as well. I kind of did it in my head. I did it shorthand. I realized that these powers of 10 would cancel, and then we have 60 over 5. And since 12 times 5 is 60, 600,000 divided by 50,000 is 12. The 50,000s cancel on that side. And so notice by dividing by the 50,000 on both sides, I end up with a simpler form of the equation. It's supposed to be a 0. So now the n up here in the exponent is a little bit of an issue. And to deal with that, we actually use a logarithm. And there are a bunch of rules with logarithms. I mean, that in an algebra class you would normally learn. Things like, you can't take the log of a negative number, and things like that. And I'm actually going to use one of the rules of the law of exponents here. This is really the only one you need to be aware of for this particular situation and the types of geometric equations we would be solving. But but one of the rules of logarithms is that if you take the log of a base to an exponent, the exponent can come out in front of the log. And the log of a number like 106 is just a number. And we can evaluate that using the calculator. So now again, I can solve here by dividing both sides again by the number log of 1.06. And incidentally, I'm just writing LOG, but the LOG log is the base 10 log. That's a convention in mathematics. But again, I'm really trying to keep this simple. I'm really just illustrating the process. So notice on the right side now I have n isolated, so I'm going to write that on the left just because that's often how we write things in mathematics, the unknown on the left or what we're looking for. Now calculators are a real wonderful thing. Back in the old days, mathematicians would rely on slide rules or tables to do these kinds of calculations. But now we have the calculator. Notice on your calculator there's an LOG key. And notice 10 to the x, the excuse me, the exponential term 10, or the exponential expression 10 to the x is above. That's because LOG is the base 10 log. Notice here we have excuse me, another logarithm key that corresponds to the e to the x key. And that's because natural log is a base e log. And again, I'm not going to get into all those really technical details here. I just want to demonstrate how to do this problem on the calculator. So I press the log, then type 12, divide by log again. 1.06. And what we find is it's about 42.6 years. Now, the same technique will apply to any situation where the population is growing geometrically. So it's fine. One thing we could say is we maybe should round this up to 43 years, since our model is based on whole year increments. But in any case, that's it. One thing I did want to point out though, before I sign off here, is notice this is a much more accurate estimate than the one we got from the graph. I think the one I had in the graph, I was saying something like 43 and a half to even 44. And actually I was off from my estimate on the graph. So using the analytical, I want to say algebraic, it's really an algebraic technique we're talking about here, to solve for the number of years gives a better answer. Okay, that's it for this video. I'll see you next time.